Okay, shall I start? Okay, so be on time, command duration limits support in Linux. So this is an HDD talk. So I'll go through some background first about HDD performance and I/O latencies. Uh, and then I'll dive into more detail of this new feature called command duration limits. So first of all, HDD performance and I/O latency. You probably already experienced that. But it's really extremely important for to get good performance with HDDs to use high Q depths. So you need to exercise your drive at high Q depths, and as you can see, the higher the Q depths, the more IOPS you can get from your drive, and you can actually more than double the IOPS from Q depths 1 to up to 32 here on an ETA drive. However, at the same time, you can see that here I have the average latency and the 99th percentile latency. As you do that, some of your commands in there, in that queue, will suffer very large I/O latency. So in average, you go from a few milliseconds to almost 200 milliseconds, and the worst case there for the 99th latency over 550 milliseconds. So sometimes not rare to even wait for a second for an I/O to complete on an HDD when you are doing this high Q depths workload, again, to get better IOPS and better throughput. But again, that high latency is a problem in many cases. You really want most of the time to control I/O latency so that you can provide user service level and QoS guarantees to your application for some I/O density aspects of the workload. It's also important. But it's also important for the overall system performance, because if you care about your I/O latency, you can actually increase performance. For example, in a RAID system or anything that is erasure coded using multiple drives at the same time, if you issue one I/O for one single user access, you need multiple I/Os to multiple drives. If you have one drive that is slower than the other in there, that's the one that is going to slow down the entire user I/O. So if you can control latency in that case, you can speed up the user accesses to that erasure coding system. And so over the years, many implementation and systems out there in the field have used different techniques. The most basic one is simply to actually reduce the Q depths at which we exercise the drive to keep control over the latency. So essentially here you're trading off performance for a better I/O latency. A few years back, the ATA NCQ Priority feature was standardized and is supported by most drives these days, which gives you a partial best effort control over I/O latency. It's not actually a direct control over the latency itself, but how fast some I/Os will be processed against others. And we have now this new feature that has just been standardized for ATA. SCSI is still in the works, but so it's called command duration limits, and that's one of these talks. So let me first quickly go through the legacy techniques that are used. First one, the most simple one, is actually to limit the Q depths. And how it works? Simple. You have this characteristic of your drive, and let's say you want to aim for at most 100 millisecond latency for your I/Os. Well, tells you, you look at here, the worst case scenario tells you that you should not go over Q depths 4. So exercising your drive, your workload with at most 4 I/Os, you will have all your I/Os within 100 milliseconds always. That's very simple, but the result, of course, is that your IOPS really drops a lot compared to the maximum you can get from the drive. This is actually very heavily used in the field by a lot of hyperscalers even today. So next feature, a bit more intelligent, is called ATA NCQ Priority. And so I said recently, but this was standardized actually 10 years ago, more than 10 years ago. And that's only for ATA. There is actually no SCSI equivalent. So that's why it's not been used so much. Because of course, if your ATA drive is behind a SAS HBA, well, you lose the ATA interface to the drive, you have to go SCSI, and you do not have that priority feature in SCSI. So what this feature defines is essentially single bit. Well, there's 2 bits, but in the end, it's really just a 1 bit. That tells the drive this is a high priority command or this is a normal priority command, so meaning low as opposed to high. That's all it does. There's no definition of what high priority means and how quickly the drive should be executing this command, which means that depending on the drive firmware implementation, you may have differences between different drive vendors and different drive models. There's really no telling how the drive is going to react to a mixed high priority, normal priority workload. So in Linux, this is supported since kernel 4.10. This uses this maps into the RT real-time IO Prio class. So this interface actually predates 4.10. I think it was added in 2.6 something. But so the AT NCQ priority feature, it's tied to the real-time class, which is the highest priority class. And you can set a priority per process, per user, or per group of processes using the IO Prio set system call. And you can also do that, so that's since kernel 4.10, per asynchronous IO using the rec Prio field of the AIO structure. The interface defines 2 things, a class and the level. So the class, again, for AT NCQ is mapped to real time. And the level is priority level within that class, which is not used in this case. So whatever the level you set, as long as your IO is a class real time, it will map into a high priority NCQ command. So one example. So this is a 128K random read workload with, I can't remember, 20%, I think, high priority commands here. So the baseline, the blue line, that's our drive doing all IOs without any priority. The pink line here is so the mix total IOPS with low and high priority. So you see there is a drop, the maximum IOPS you can achieve. There is a cost to issuing these high priority commands. And so the IOPS here for low and high priority. So yeah, I think it is 20%, the workload is 20% high priority IO. But if you look at the latency, you can see clearly that the high priority IO maintain a very low latency. Everything is executed under 50 milliseconds. But that comes at the cost of an even higher latency for your normal priority IOs. So compared to the baseline, it's even higher because, again, the drive to be able to quickly execute those high priority IO has to delay normal priority IO. So you end up with up to 700 milliseconds here latency on normal priority IO. So very fast for high priority, but everything gets slower overall, so lower performance, and also higher latencies for normal priority IOs. So that has been considered a problem out there because it's not really flexible, and also the fact that all you can tell the drive is this is high priority without any really hint as how quickly you really want those IOs to be executed. The work on this new standard called command duration limits has been done to define a more advanced interface for controlling IO latency. So this time, this was done both for SCSI and ATA, so both standards have an equivalent definition of the feature. For SCSI, it's defined in T10 SPC6, so it's not limited to hard disk. It's SPC, so hard disk as or SBC. You can actually apply that to different classes of SCSI devices. And for T13, it is defined in ACS5, which has been forwarded to INSIT for standardization, so it's completely approved. SPC6 is still a bit buggy. The document is buggy. There's updates needed there, but we're getting there. So what command duration limits does is define a set of 7 command descriptors, 7 for read commands, 7 for write commands. These are defined through log pages or mode pages, depending on if you're SCSI or ATA. And 3 bits are added to read and write commands. These 3 bits point to the command descriptor that should be applied to the read or write command. And the important part here is the drive doesn't define itself these command descriptors. The user can set them. So it's completely configurable by the user. The user can change the command descriptor. And so what the command descriptor do is define limits, time limits for command execution. And there are 3 different limits that are defined. The first one is kind of the simplest to understand, which is the command duration guideline, which is the maximum command overall execution time for the command, the time target. You do not want to exceed that limit for the command execution. There's 2 other limits. One is the maximum inactive time, so you can tell the drive, I do not want that command to stay in your queue more than X millisecond. And the maximum active time, which tells the drive, do not spend more than X millisecond trying to actually execute on media that command. So that's actually an interesting one, since hard drive may spend a lot of time trying to process a read or write if it hits a bad sector. If there's a defective sector, a read, for example, may be retried many, many times, so that with different level of ECC and signal processing until it actually gets the data right. And so you can limit that amount of retry that the drive does with this limit. Frankly speaking, I'm still having a hard time seeing where the maximum inactive time limit can be effectively used, but it is there, it is defined. So furthermore, for all these limits, for each one of these limits, the descriptor also defines a policy to apply to the command if the limit is exceeded. So if the drive reaches a point where one of the applied limit is exceeded, it will do one of these. So the first one, simplest one, is best effort, meaning that, okay, I tried, I failed, I'm going on. So you're going to exceed the limit, but nothing will happen besides the user seeing a slightly slower command. So the command will still normally complete if there are no other error. Second policy is continue limited. So in that one, it's going to switch descriptors. So say you issue the command with descriptor 1, which has a particular set of limits. If it misses that, it will continue processing the command, but applying the next descriptor in the list. So descriptor 2, which may have a different set of limits. So depending on how the user set that, it may actually end up being a timeout right away or slightly extending the previous limit. Next one is continue no limit. So it's kind of like best effort. You simply ignore the limit. You just continue executing the command without any limit. So meaning that it's the command at that point essentially becomes the same as a command that has no limit in the first place. So it's slightly different from best effort, because in the case of best effort, you continue, but the drive will still kind of assume a high priority for that command for which you missed the limit. And then there are the 2 fast fail that we call them fast fail command. which are going to be aborted by the drive. So the last one, called abort, is actually a simple one. You'll get back an error. The drive is going to tell you command timeout. So it didn't work. The complete one is a bit tricky, and that was defined actually because of ATA peculiarities with I/O errors, which is that on ATA, when you're exercising your drive using NCQ command at the high queue depths, if one of the command fails, the entire queue is aborted. So the entire command set goes back to the host. The host figures out which command failed and resend the one that didn't fail, which is of course costly. That stalls the queue depth. The drive queue is stalled, so you lose time. You do not do I/O while you're processing that error, and that is costly in terms of performance. So this abort is actually an abort with a good status. So it doesn't say error, but it does attach sense data to the command saying data currently unavailable. So you get back a success, but there's no data. So you really have to be careful checking that one, because otherwise you'll deal with garbage data in your buffer. So Linux integration of this. We simply reused the I/O Priority API, so same as NCQ. And for that, we defined a new priority class, I/O Prio class DL, so duration limit. And since for any priority class we have different level, for that particular priority class, the level specified the descriptor to apply to the command, to the I/O. So very simple. That matches very well. 8 priority levels for most levels here. So we use the same value since we have 7 descriptors plus 1 that says no limit, so no descriptor. That match extremely well this feature. Same way of specifying I/O. Specifying limits per process, per group of process using system call, or per I/O with the asynchronous I/O interface. The limits are actually exposed through sysfs, so the user can consult the different limits and policies apply for each descriptor for read and write. So it's under the device attributes. There's a new directory there, duration limits, that lists everything. And there's also an enable flag there that can be set to enable the feature or not. FIO has been patched to almost. There is one more patch to define that new priority class to be sent, but there are many options to FIO, like the command priority percentage thing that allows you to define very complex workloads with different limits to test things. So here's one example. And in this example, we use a descriptor with a very short limit, 50 milliseconds, I think it is, 30 milliseconds actually, with a best effort policy, just to try to replicate what NCQ priority does. And so, what did I print here? So, 30 millisecond limit, as you can see, when you go high queue depth, you're a bit over 50 milliseconds. So the drive is missing some deadlines there, but it's essentially equivalent to what NCQ priority give you, the previous example I gave. The big difference, though, is that now the drive knows about that 30 millisecond limit, and so can do a better job at internally scheduling commands. And what you can see is that the no-limit IOs don't get a big hit going up to 700 millisecond worst latency. They actually are better off compared to the deadline. Overall, the drive is really doing a much better job scheduling internally commands because it has more information thanks to that 30 millisecond limit that it knows about. So you can now combine different limits for a different set of IOs. So here it's 10% of the commands with a 100 millisecond limit and 20% with 200 millisecond limit. And you can see that the drive essentially maintains the completion latency for the commands that have these limits. The 100 millisecond, again, you get a bit of miss, so it goes a bit over 100 millisecond here for large IO QDAPs. But again, we get the benefits for no limit IO that don't get a huge hit on the worst latency here, maintaining something very decent, actually much even better than the baseline where you do not use any priority or any limit. So the previous example, if you do the same using NCQ priority, sorry, not the same, but an equivalent workload using NCQ priority, meaning that you essentially specify 30% of your commands with a high priority, you can see that you end up with a much worse case scenario for those commands that you want within 100 milliseconds. You're way over there because, again, NCQ doesn't specify the limit, so you don't know. The drive doesn't know and just does its best. And again, large hit on the worst case latency for low priority commands. Another example here with 3 different classes. So you see again, we have 100, 200, and 300, and you see the flat lines here showing that the commands are processed as asked for by the user, by the drive. Okay. So command duration limits, much more flexible than NCQ priority. It's equivalent in the sense that you can always set a descriptor with a very short limit that will emulate essentially what NCQ priority does. But you can go further, define more descriptors, different limits. You can actually tune how fast you want your IOs. That impacts also the max IOPS that you will get. So the larger the limit, the better the IOPS. So you can trade off depending on your workload. And this feature actually enhance the NCQ priority feature itself also because you have the possibility to use the first descriptor of that list of 7 descriptors to define the limit you want for a high priority NCQ command. So the 2 features are not compatible. You cannot use them at the same time. So for a drive that supports command duration limits, if you keep using NCQ priority, you can simply set that first descriptor to tell NCQ high priority, okay, use 100 millisecond limit or 50 millisecond. So you can actually now tell the drive how fast you want your IOs for the high priority bit. The fact that we very simply reused the Linux IO priority API, it's easy for application to migrate from NCQ priority to this new feature. There is also possibility to integrate that deeper into the Linux kernel, especially we're thinking about C groups where there is the latency controller for I/O. So if we can tie that to C group and the C group actually setting the descriptor, that would be a good match there too. And this is still ongoing work, not upstream yet. We've done the block layers, SCSI layer is done. libATA I/O error handling needs some work because of that good status completion that needs some special handling. ATA doesn't have auto sense. You don't get the sense data attached to the command back like SCSI, so you need another command to go get the sense data for the command to check if it's a real good status, meaning that the I/O was really done, or if it's one where you get data unavailable sense returned from the drive. So we expect to send that out for 5.19, so to queue for 5.20. It's coming soon. That's it. Any question?
So are there any plans to make the kernel do anything with this automatically? It seems like you could implement scheduling policies in the kernel to just make things generally better.
Yes, we could. So C group is the best place to do that, I think, because C group actually, so the latency control in C groups has the notion of latency. The block IO scheduler layers, so BFQ and MQ deadline actually do support IO priorities, but just that, priority. The scheduler doesn't know what the semantic attached to priority, essentially. So you would have to go and get that list of descriptors, look at the deadlines, at the limits, to understand how to best schedule the commands. So that is a lot of work. I think the C group C group approach is a lot more sensible.
But if you're exposing all these configuration knobs to user space, that means the kernel account, as you say, they do its own thing, right?
Right now it's not. It's really through, just attached to the user space using the drive directly is just passing along the information about the descriptor and set that in the SCSI command. That's all it does. The kernel itself will not do anything. We did patch a little bit BFQ and MQ deadline so that any command that has the class DL is handled exactly the same as class real time. So internally in the blockhouse delivery, it's handled as class real time. But among those commands, those that have different limits, potentially longer limits, they are all exactly handled the same way. So there's no differentiation yet.
So you only have 7 descriptors, right? That's
Yes.
the standard. Would it make sense to reserve one of them for future internal kernel use? Because once you're exposed into user space, it's API.
We could, but it's always tricky because depending on your workload, what is it exactly you really want? So the user having access to everything, at least to set it, is most like the most flexible approach, I think. So we could, as a spec, say, okay, descriptor 1, the first one is going to be used by file system for metadata, for example. Second one for regular data IOs. The other ones are yours. Do whatever you want with it. Yeah, that could work, but again, it's hard to automatically set sensible values for these first two if we keep them for the kernel use. So showing that to the user, yeah, I'm all for it.
Final question, the pretend you completed, is that only for reads, or can you do that for writes as well?
For writes as well, yeah. But yeah, it's not really,
Then you can
doesn't make really much sense, but yeah, you
If
can.
the kernel can retry, then you're basically down to networking and you can do cutoff.
So the limit on writes are not very sensible because if you're running with a drive write cache, it doesn't really matter much. It's really mostly for read.
Okay.
Yes?
What about the support for hardware rates with sort of write back cache and so on?
So this feature is also defined for SCSI, so any RAID system these days they are all SCSI.
They need to solve the same problem themselves,
So
propagate it through.
the host to the RAID controller, the interface is going to be the same.
Yeah.
What the RAID controller does with the limits and how it propagates that to the different drive in the RAID array, that's the controller problem. So it has to handle that itself. How that's managed, yeah, that's the control problem. The host sees a disk which is a RAID volume, but it doesn't really know that.
Do you know
That's
if
it.
there is a RAID controller that is working with this?
Not yet. That's really just really starting. The standards have been finished. Linux support is not upstream. I have some HBA vendor who contacted me to get actually the early code so that they can start working on their HBA because you need HBA support for that too, so that the bits are properly propagated. So it's coming. So yes, we may see some RAID vendor working on that in the future. Yes.
Seeing the numbers here, I think this is all about mechanical path writes.
Yes, it's the.
So is there any plans to do this for SSDs where you need to do this like I want this back in half a microsecond or something?
Very good question. Yes, there is interest in the NVMe space for that. There's a bit of problems though with this the interface as it is because so for example as far as the host is concerned, an I/O starts when you put it in the submission queue. But for the device, the I/O starts only when it fetches the command from the submission queue. So whatever time the command spends in that queue, that's not accounted as inactive time. So see, the limits don't really match the physical characteristic of the protocol there. So there are ideas though floating around to define, for example, one submission or a queue pair per limit, which would make more sense and easier, so that the drive the device doesn't have to fetch all commands before to know what limit to apply to them. So ideas like this. There is, for a PCIe device, we're not really, we're still thinking if it really makes sense. There is, however, a lot of interest in the fabrics world, so NVMe with TCP, when you have multiple links especially, you would be able, if you have limits attached to your commands with multiple links, you could, for example, schedule your commands over the different links depending on the link speed you have. You can also do something, improve link aborts when you get a link dropped in your multipass setup. If you have limits, you can actually better handle retries of commands, give up or not, etc. There are several ideas, so we've started talking with many different people about where this would make sense for NVMe. But yes, there is interest. There is also interest because NVMe HDDs are also being considered today. HDDs with an NVMe interface, so we would need to have that feature to keep backward compatibility with SCSI and ATA. But again, because of the different characteristics of the protocol, it needs to be tweaked a little bit. Yes?
Why do we even have retry commands? We should have perfect signal integrity.
Yes.
That was a joke.
I mean, no, it's not a joke. I mean, I totally understand because actually if the drive gives you back an error on the read, retrying is more useless. So, yeah, we could stop retrying in the kernel. Actually, the retries are not for all errors though. If you look carefully at the SCSI driver, you'll see that it looks at sense.dat that describes the error, and it will not necessarily retry for everything. So, it depends on what the error is. And I'm not entirely sure if you get a bad CRC, it's going to, for example, give up right away. Good. More question? Thank you.